Hello there, and welcome back. In our exposure to elementary statistics and probability theory, there were several assumptions that we were using for a lot of the hypothesis tests and models that we were using to model phenomena in both statistics and probability. One of those assumptions were independence. In this video, we're going to be focusing on how to test for independence via what is called the chi-square test for independence. So let's just write down a couple things that are sort of going to guide this discussion. Firstly, the guiding question that we're going to be exploring today is how can we assess the independence between two or more random variables. Right, so that's going to be the question that we're going to try to answer today. So let's just recall a couple things from basic statistics that we definitely should know in order to conduct this conversation. So firstly, if x and y are numerical random variables, so not categorical, then if x and y are independent, then a few things are going to hold. Then the covariance between these two random variables, x and y, is going to be equal to 0. And remember, if the covariance is equal to 0, this is going to be true if and only if the product moment between x and y is going to be equal to the product of their first moments, expected value of x, and the expected value of y. Also note that this also gives us another relationship. So also note, if the covariance between these variables is equal to 0, then this is going to imply, biconditionally, that the correlation between these two variables, remember, is just equal to the covariance divided by the product of the standard deviations of those two random variables. That's also going to be equal to 0. So a very important thing that you need to keep in mind here, so very important, if the covariance between these random variables is equal to 0, that does not necessarily imply that x and y are independent. But if the covariance between them is not equal to 0, then that does imply that x and y are not independent. And keep in mind that this is a theoretical observation, not an empirical one. So if you have an empirical covariance that is equal to 0 or something close to 0, that may provide evidence that the two variables are independent. But keep in mind that if the covariance is 0, it does not necessarily imply independence does exist. So you should see some connection between variance and independence, and indeed there is an intimate connection between them. So clearly, independence and variance are connected. That is at least one observation that we can make from these properties, right? So also keep in mind, if x and y are independent, then a lot of properties are very nice for example, the variance. So if x and y are independent, then the variance of x plus y is just going to be equal to the variance of x plus the variance of y. And that's because this 2 covariance x and y term actually doesn't exist, because if they're independent, that term is equal to 0. Right? So what is the difference between these two expressions, in particular the left and the right? So the left studies the variation of x and y in isolation of one another, so you can study x and you can study y independently, or you can study both simultaneously. Potentially in the same exact environment. So if you can prove that these two variables are indeed independent, then that means you can study these variables in isolation of one another, and that will be, of course, equal to the same exact result as if you were to present both of them next to each other. The results should be the same. And if they're not, then it is just by chance. So, of course, these are just some observations that we need in order to sort of motivate the discussion of the test for independence. Now let's get to the main point of this conversation. In order to start the construction of the chi-square test for independence, It's going to be very easier to construct it or construct the motivation of it if we just consider two events, x and y, and let's assume that they're going to be in the same sample space S, and we're going to assume that these events could either take one of two states, success or failure. In general, we're going to extend this to more than two events, and of course we can assume those states could take more than two forms, not just a binomial outcome, but say a multinomial outcome, or possibly infinitely many, who knows. So let's just define a couple probabilities in this particular discussion. Let's assume that the probability that x does occur in terms of a success, let's just call that px. And let's assume that the probability that x does not occur in a success, that's of course 1 minus px, but I'm actually going to find that to be equal to qx so that we can easily extend these to the multi-outcome case. Similar for y, we're actually going to do it in a very similar manner. So the probability of y occurring in a success, let's just call that py, and the probability that y does not occur in a success, so the probability of failure for y, that's just of course going to be equal to 1 minus py, but we're going to be defining that to be equal to qy, so that again we can easily extend it later. Let's also create a little table to summarize all of our outcomes. So we have 4 different outcomes in this scenario, right? So we have events, x and y, and those events could either result in a success or a failure, right? So the probability of success for x, that's going to be px. The probability of failure, that's going to be equal to qx. Probability of success for y, that's going to be equal to py. And the probability of failure for y, that's going to be equal to qy. We're now going to be looking at the totals of these rows and the totals of these columns, and also the grand total, that's going to be that bottom corner box. So the probability of x occurring, is either going to be px or qx, and of course they are mutually exclusive events, so we don't need to subtract any intersections. And the probability of y occurring, so y could occur in either a success or a failure, so that of course could be py plus qy. And the probability of success occurring, so that either could occur via x or via y, that's going to be equal to px plus py. The probability of failure occurring, regardless of the event, that's going to be equal to qx plus qy. And the probability of any outcome occurring, that's going to be equal to px plus qx plus py plus qy. So that's going to be the grand total of all of the values in this particular box. So this sort of corresponds to the probability of the sample space. So those are sort of synonymous here. So what is the goal of testing for independence? So let's phrase this from the perspective of hypotheses. So our goal is to test the claim. So what's the claim? Let's use the claim that x and y are independent, and the alternative, x and y are not independent. We don't really care about the strength of the dependence. We're just going to try and prove that they are dependent on each other regardless of direction. So that in disguise is a two-sided alternative. Right? So what we're going to do is we're actually going to begin by focusing on cell 1. So we're going to be focusing on row 1, and we're also going to be focusing on column 1, so that particular cell. All right, so what is the probability of x occurring? And let's assume these possibly are counts, right? So this could be equal to the probability of x or not x, right? So either it is a success or it is a failure, but regardless of it, that's the occurrence of x, all divided by the total probability, so it's going to be px plus qx plus py plus qy, right? So that's going to be the size of the event space over the size of the sample space. And similarly, what is the probability of success? So that's going to be the sum of column 1. So because that success could either occur in x or y, so that's going to be px plus py all over the same exact total. So px plus qx plus py plus qy. Okay, now this is important. So let's consider the event x and s, right? So that should be equal to px divided by the quotient, right? So if they are independent, and that's a really big if, that should be equal to the probability of x times the probability of s, right? So what is the product of these two probabilities? So that's just going to be equal to px plus qx times px plus py all over px plus qx plus py plus qy quantity squared. And technically, this sum corresponds to the grand total of probabilities. I'm going to give that a new name. I'm going to call that capital M, and therefore I can rewrite the probability of this product as simply px plus qx times px plus py all over n squared, right? So sometimes, it's very important to know, sometimes proportions, either p or the sample proportion p hat, can be misleading. And let's just recall what the sample proportion is. So if we look at the population proportion, for example, that's going to be capital X over N, so the number of total successes in the population divided by the population size, and p hat is going to be X divided by sample size, so that's going to be the number of observed successes all over the population size. So it's sometimes more reliant to just focus on the number inside of that ratio. So how can I instead transform this from a ratio into just a count of successes or observed successes? I can just simply multiply both sides of this equation by n, and that bottom should be equal to little n, of course. And that's going to give me the observed number of successes. We're focusing on the theoretical form, therefore we're just going to be multiplying both sides of this equation by n. So if that is the case, that means the size of x and s, that's just going to be equal to px times py times the population size, or the total number of occurrences. So that's just going to be equal to px plus qx times px plus py all over n. Now, I just want to make this very clear before I extend this. What are we actually looking at? So we're looking at the observed number of successes, or occurrences rather. So the number of occurrences in cell 1-1. So we're looking at this particular region here. And what is px plus qx? That's just the sum of row 1. Px plus py, that's just the sum of column 1. So we can actually write this. So the sum, or the size of, let's call it cell 1-1 just for short. So that's just going to be equal to the sum of row 1 times the sum of column 1, all divided by the sum of all cells. And this gives us a framework or motivation to extend it to not just the first cell, but for either of them. But the big assumption in the derivation of the structure is that we are assuming that they are independent, which is what we're trying to test, right? So if x and y are truly independent, this property, the one shaded in this box, should hold not just for one cell, but for all cells. And now you can sort of see how I can expand this to more than two events and more than two outcomes, right? So now I'm going to define this next term, which is the generalization of that box term. So this is going to be represented as E subscript jk. So that's going to be the row number, and k is going to be the column number. So this form here, this is going to be equal to E11, for example. So ejk is going to be equal to the sum of row j times the sum of column k, all divided by the sum of each of the table values. So the total, that's the grand total, I guess you could say. So this formula, what does this formula represent? So this is the expected number of occurrences in cell jk if all variables in question are independent. And then we can compare the expected value and the observed value for each of the cells, and then that can give us some, at least, direction on how to test for independence. So let's actually take a couple numbers and a few examples to sort of see how that would look in practice. So let's suppose you are interested in studying if there is some connection between age groups and the hours per day a person spends on their cell phone. So let's assume we want to break up our age categories into 18 to 22, 23 to 28, 29 to 40, 40 to 55, and 56 and older. Similarly, for the amount of time per day that people spend on their cell phones, let's assume one category is 0 to 1 hour, 1 to 3 hours, and at least 3 hours per day. So let's assume we go out and survey a number of people that fall into one of these categories. Now let's assume that 15 people between the age of 18 to 22 spend less than 1 hour on their cell phone. Similarly, 32 of that age group that we observed spend between 1 and 3 hours per day on their cell phone. And let's assume that 42 of the people observed spend more than or at least 3 hours on their cell phone. So we could, of course, do this for every single age category, and let's just create some numbers here. Let's let this be 14, 19, 9, 18, 28, 23, 11, and 15, and then 36, 21, 14, and 9. So if these are all of your observations, from this data, do we have evidence to believe that there is some connection between age group and the amount of hours per day a person spends on their cell phone? Or pretty much what we're asking is, are these two variables independent or dependent? So let's look at the totals for each of these sums and rows. So the total for each of these rows is going to be equal to 89, 78, 63, 34, and 42. So this is definitely an Excel-friendly type of test. The sum of each of the columns are going to be equal to 75, 109, 122, and then we're going to have a grand total of 306. So that's how many people we had in this particular survey. So what is this column? This table represents the observed occurrences. So OJK corresponds to the observed number of occurrences. Observed number of occurrences. All right. So what are the expected number of occurrences in each of these cells that would occur if these variables were independent? So let's just go through that calculation. So remember, E11 should be equal to the sum of row 1 times the sum of column 1 divided by the grand total of 306. So that's going to be equal to 89 times 75 divided by 306, which is going to be approximately equal to 21.8. Similarly, E21 or E12, so first row, second column, so that's going to be equal to the sum of row 1 times the sum of column 2, all divided by the grand total. So that's going to be equal to 89 times 109 divided by 306. That should be approximately 31.7. And we're going to do this for all of the 5 times 3 equals 15 different cells in this table, and that's going to generate a new table, which is going to be our expected observations. So the expected number of occurrences. So the expected number of occurrences if these variables of study are independent, right? So what were our categories? So that was going to be equal to less than or equal to 1, 1 less than y, less than or equal to 3, y greater than 3. So those were our cell phone time categories. And then we have 18 to 22, 23 to 28, 29 to 40, 40 to 55, and then 56 plus for those categories. So I'm not going to bore you with me filling out this table, so let me just pause this, fill this out, and then we're going to get back to the analysis part of it. Now that we have our expected table for the number of occurrences for each of these variables, assuming that these variables are independent, and we also have the table of observed occurrences that we obtained from our sample. Now we need to answer the question, are these numbers cell by cell significantly different from the rest? Right? So now we need to figure out, is there a way that we can answer that question? So let's just formally state that. So question, is there a significant difference between the observed value for each cell and the expected value of each cell? Now this question should be very familiar to you. Is there a significant difference? Aha, we've done hypothesis tests on this before, right? So we're going to be comparing 21.8 to 15. We're going to be comparing 31.7 to 32. We're going to be comparing 35.5 to 42. We're going to be comparing 19.1 to 14, and so on for all of the cells. Now, what is a very good way to do this in a way that pretty much is similar to something else that we've already done? So what I'm going to do in terms of test statistics is we're going to do a weighted sum of squares, or weighted sum of squared differences. Because then we can use like an analysis of variances to analyze the differences between them, right? So we're going to create our test statistic I. So I is going to be the sum of OJK minus EJK squared, all divided by EJK. So if you do this, so if you do, for example, 15 minus 21.8 squared divided by 21.8 plus, you do the same for all of the other cells, you're going to find that that's going to be approximately equal to 16.502. So in a way, this is a measure of variation. So the question is this too large or too small? So which question should we be asking? Well, if OJK and EJK are equal or approximately equal to each other for all of these cells, that means this difference should be close to zero, right? So if there is a significant difference, that means this metric, I, should be significantly large. Well, how large? Well, we should be able to construct some critical value to sort of benchmark that, sort of like we did with confidence intervals and test statistics and p-values back in the day. So let's just look at this from the hypothesis testing perspective and see if we can construct an equivalent numerical way of testing independence. Right? So is x and y, well, if x and y are independent, then I should be approximately equal to 0, right? So that means the null hypothesis that x and y are independent with a two-sided alternative that x and y are not independent is equivalent to the null hypothesis that I is equal to 0 with the alternative that I is greater than 0, right? Because this metric cannot be negative. So it's very important to keep in mind here that this is going to be a one-sided or one-tailed alternative. So you definitely should be familiar with how to conduct one-tailed test in order to continue this. So now we have a test statistic. We have our alternative hypothesis that we're going to be using to test this. Now we need to compare this test statistic to something. So the next question, what critical value do we compare this number I to? Right? So it's very important that you note that this metric is very similar to what other metric of variation? This is really close to variance, actually, because keep in mind, the expected value is sort of like a mean, right? So this is sort of like a mean. OJK is the observed values, that's pretty much like x, and then we're squaring it, and then we're just sort of adding them up, and we're weighting it, so it's sort of like a scaled down version of this, right? So this is sort of like a variance. So if that's the case, what type of distribution model's variance in terms of hypothesis testing, that would be chi-squared critical values. And now you see why the test for independence is called a chi-square test for independence, right? So that gives birth to this test, right? So the chi-squared test for independence. So what does the chi-square distribution look like? So let's just take a quick moment to remember that. So that's our skewed right distribution, which is generated from a sum of squared standard normal random variables. And remember that this critical value is what we need to figure out, right? So that's our chi-squared critical value. And this should be some level of confidence C, and this is our alpha region over here, right? So if our test statistic is here, so if I is less than our chi-square critical value, then we're going to be failing to reject the null hypothesis. So if we fail to reject the null hypothesis, that means we're implying that x and y are not independent. Now that's case 1. So if case 2 exists, so if I is greater than our chi-square critical value, then we're going to be rejecting the null hypothesis. That means we have evidence to believe that x and y are independent. Now keep in mind it doesn't imply that they are independent, but we have evidence to believe that they are independent. All right, so now that we have some basic fundamentals here, let's make up some numbers so we can conclude this test. So let's assume we want a type 1 error to be equal to 12.67%. If that's our level of significance, that means our level of confidence is going to be 87.33%. Then we can find out our critical value. So what is our degrees of freedom here? Because we need that in order to construct this hypothesis test. So the degrees of freedom for this chi-square test of independence, so the degrees of freedom, which is usually abbreviated by V or nu, is going to be equal to the number of rows minus 1 times the number of columns minus 1. So remember, how many rows did we have? So we had 1, 2, 3, 4, 5 rows. And we had 1, 2, 3 columns. So if that's the case, then the degrees of freedom for our test is going to be equal to 5 minus 1 times 3 minus 1, which is 4 times 2, which is 8. So that's our degrees of freedom. So once you have your degrees of freedom, you can find out this distribution. So this is a chi-squared 8 distribution. Then you can find that critical value since we know our alpha value and our C value. So you can find that our chi-squared critical value is approximately equal to 12.5915. Now that we have our critical value and we have our test statistic I, what was I? I was approximately equal to 16.502. 16.502. So our test statistic is outside of our fail to reject region. So that means since our test statistic for independence is greater than our critical value, we're going to be rejecting the null hypothesis that they are independent. That means what? We have evidence to believe that there is a connection, is some connection, or dependence rather, dependence between age groups, and cell phone use. And that is what we call the chi-square test for independence. And notice you can easily extend this for a lot of rows and a lot of columns, so there definitely is a lot of flexibility to be used here. Now, interesting question, can you study more than 2 different dimensions for this particular case? For example, rows, columns, and say rows in another dimension, right? So a 3-dimensional table, or possibly even higher than 3. That's another discussion for another day, but this at least gives you some basis for testing 2 variables and seeing if there appears to be a dependence or independence between them. I hope you enjoyed, and I'll see you in the next video. Take care.